Hello students, in this video we are going to see data encryption standard, initial permutation, DS round structure, substitution boxes, key schedule and decryption. The initial permutation given in the table is interpreted as follows. The input to a table consists of 64-bit numbered left to right from 1 to 64. The 64 entries in the permutation table contain permutation of the numbers from 1 to 64. Each entry in the permutation table indicates the position of a numbered input bit in the output, which is also consists of 64 bits. Numbers from bit 1, that is leftmost significant bit, to 32, 48, 64 bits etc. to the rightmost least significant bits. Note that the examples are specified using hexadecimal. Here, a 64-bit plaintext value of the given number 675A696758E5A6B5A, which is written in left and right halves. After permutating with the input permutation, it becomes FFB219 and the number which is shown here like this. DES round structure uses 32-bit left and right halves. Here we show the internal structure of DES round function F, which takes R half and subkey and process them through E and add subkey S and P. This follows the classic structure of a Feastal cipher. Note that the S boxes provide the confusion of data and key values. The permutation P then spreads this as widely as possible, so each S box output affects as many S box inputs in the next round as possible, which giving a diffusion. Next we will see about DES round structure. The picture which is shown here is the internal structure of DES round function F. The R input is first expanded to 48 bits by using expansion table E that defines a permutation plus an expansion that involves duplication of 16 of the R bits. The resulting 48 bits are XORed with Ki. The 48-bit results passes through a substitution function comprising of 8 S boxes, which each map 6 input bits to 4 output bits, producing a 32-bit output, which is then permutated by the permutation function P. The substitution consists of a set of 8 S boxes, each of which accepts 6 bits as input and produces 4 bits as output. The first and last bits of input to box Si form a 2-bit binary number to select one of 4 substitutions defined by the 4 rows in a table of Si. The middle 4 bits select one of 16th columns. The decimal values in cell selected by the row and column is then converted to its 4-bit representation to produce the output. The DES key schedule generates the subkeys needed for each data encryption round. The 64-bit key input is first processed by permuted choice 1. The resulting 56-bit key is then treated as two 28-bit quantities C and D. In each round, these are separately processed through a circular left shift rotation of 1 bit or 2 bits as shown in this picture. These shifted values serve as an input to the next round of the key schedule. They also serve as an input to permutated choice 2. DES decryption does the reverse process of DES encryption. As with any Feastal cipher, DES decryption uses the same algorithm as encryption, except that the subkeys are used in reverse order from SK16 to SK1. If you trace through DES overview diagram, which is shown here, we can know that the decryption step on top to bottom with the reversed subkeys, which undoes the equivalent encryption step moving from bottom to top. Next is avalanche effect. A desirable property of any encryption algorithm is that a small change in either a plaintext or the key should produce the significant change in the ciphertext. In particular, A change in one bit of plain text or one bit of key should produce a change in many bits of the ciphertext. If the change is very small, this might provide a way to reduce the size of the plain text or key space to be searched. DES exhibits a strong avalanche effect. In the picture, we can see that input is changed by a 1 bit, whereas the hash sum, which is the output, is changed completely. Fine, we have come to the end of this topic. We will see the next topic in the next video. Thank you.